Well, hello and welcome again to our journey into complex analysis. And in this section 2, we're going to look at complex differentiation and the Cauchy-Riemann equations. So we want to find a way of defining the derivative for complex functions, and so what we do is we simply take the definition that we normally have for real valued functions for the derivative, and we simply replace everything with complex variables. So we're going to say that a function f mapping the complex numbers into the complex numbers, which is defined in some neighbourhood of a point A in the complex numbers, we're going to say it's differentiable at A if the limit of f of A plus h minus f of A over h exists as h goes to 0. Now the difference here is, of course, that h and a are now complex numbers. They're not real numbers anymore, and if this limit exists, we as usual will denote it by f dashed of a. Now since h takes complex values, this limit must exist as h approaches 0 in any direction, because h itself is a complex number. So this is a rather strong requirement, as we'll see. If, for example, if we take the function f of z is z bar, then this is nowhere differentiable because this limit, as we'll see, is not going to exist. So if we plug it in, we take a plus h conjugate minus a conjugate over h. The conjugate splits and the a conjugates cancel, and so we just end up with h bar on h, and that limit does not exist. That is very easy to show, because you simply write h as, say, x plus iy, and then you let x and y go to 0. And if you'd go in one direction, if you let y go to 0 first, then x go to 0, you get a different answer than if you let x go to 0 first and then y go to 0. So a little exercise to show that this limit does not exist, which means that this function z bar is nowhere differentiable. Now you can similarly check that neither of the continuous functions, the real part of z or the imaginary part of z, neither of those are differentiable. That's a nice little exercise to do. And so we have the surprising result that both of these functions are continuous everywhere, but they're differentiable nowhere. Now you can cook up examples of such functions in real calculus, but they are in some sense fairly pathological. There's the famous Weierstrass function that has that property, but it's defined in terms of an infinite series. Here we're starting off with things that look fairly harmless, z bar and real part of z and imaginary part of z, which have these horrifying property that they're continuous everywhere but differentiable nowhere. Now again, as a little exercise, it's very easy, exactly the same as in real variable calculus. You can apply this to z to the n, where n is an integer, and if you do that, that quickly shows that this function is differentiable, and its derivative is, thank heavens, n times z to the n minus 1, as you might expect. So this is very useful because we see also that differentiability, if you've got two differentiable functions, then their sum, difference, product and quotient are differentiable, provided you're not dividing by 0. And that's going to tell us that polynomials in z are differentiable everywhere, and rational functions in z are differentiable everywhere, which is nice. A more interesting question is, what is happening to the real and imaginary parts of this f? And we have the first of many, I say, surprising results. And that is, if f equals u plus iv is a differentiable function at some point z, then the partial derivative of u with respect to x equals the partial derivative of v with respect to y, and the partial derivative of u with respect to y is minus the partial derivative of v with respect to x. Moreover, the derivative is simply given by u sub x partial du dx plus I partial dv dx. Now these two equations here are called the Cauchy-Riemann equations, and they're really the basis of all complex analysis. So much follows from these two remarkable equations. I'll do an example in a moment. Let me just quickly go through the proof as to where these things come from. So the idea is to let h, we're assuming that the function is differentiable, and that means that limit, that quotient limit, must exist as h goes to 0 in any way we like. And so I'm going to let h go to 0 in two specific ways. That is, I'm going to firstly send h to 0 along the real axis, and then I'm going to do it along the imaginary axis. So initially I'm going to take h to be real, and then I'm going to let h go to 0. So here's the difference quotient, f of z plus h minus f of z on h. I'm going to split this up now into its real and imaginary parts, so I get u of x plus hy minus u of xy plus I times the v's, and still dividing by h. Now we're thinking of h here as real, and so at this point this difference quotient here is real, and if I let h go to 0 on this one, then that will give me the partial derivative of u with respect to x. And similarly here, if I let h go to 0 on this difference quotient, then this will give me the partial derivative of v with respect to x, and I've got an I multiplying there. So if we take h to be real and let h go to 0, then this difference quotient goes to u sub x plus iv sub x, which is going to be our derivative, in fact. Similarly, if I take h on the imaginary axis, so I'm going to write h to be ik, where k is real, and I'm going to let k go to 0. Then again, we do the difference quotient on this one. So pulling the 1 over I out for the moment, well, looking at the second difference quotient here, then as h goes to 0, sorry, as k goes to 0, this bit over this is going to go to partial dv dy. It's the second variable being differentiated with respect to. So that's that one, because the i's cancel there. And then plus 1 over I. Now 1 over I is the same as minus I. And this difference quotient is going to go to partial partial du dy. That should be u sub y there. That's partial du dy. Now the point is that these limits should be totally independent of which way h goes to 0, because the function is differentiable, and so we can equate these two. So equating the real parts, we get v sub x is u sub y, and equating the imaginary parts, we get v sub x is minus u sub y, or if you will, u sub y is minus v sub x. And they were our Cauchy-Riemann equations. So, as I mentioned, if f then is differentiable, these limits are equal, and equating real and imaginary parts, as we saw, gives the Cauchy-Riemann equations, and we've also get the formula for f dashed out. And by the way, now you can see why z bar and so on are not differentiable, because z bar, for example, is equal to x minus iy. Z bar is x minus iy, so u is equal to x and v is equal to minus y. And if I do partial du dx, I get 1, and partial dv dy is minus 1, and they're not the same. And so we can see why z bar is not a differentiable function, and you can similarly see why the real part and the imaginary parts are not differentiable, because their real and imaginary parts do not satisfy Cauchy-Riemann equations. Simple example here, just to verify that the real and imaginary parts of this cubic polynomial satisfy Cauchy-Riemann equations. So all I do is I put z equals x plus iy in. So I've got to cube it and subtract off twice the square of x plus iy plus 4 brackets x plus iy minus 2. Take a deep breath and expand it all out. And then you pull out the real part, which looks like this. And you pull out the imaginary part, which looks like this. Nice little exercise to do. And let's just check Cauchy-Riemann. If I differentiate this one partially with respect to x, you can see I get 3x squared minus 3y squared minus 4x plus 4. And if I do this one with respect to y, I'll do this one with respect to y, then I'm going to get 3x squared minus 3y squared minus 4x plus 4. And notice that these two are the same. If I differentiate this one partially with respect to y, I get minus 6xy plus 4y. And if I do this one partially with respect to x, then I get 6xy minus 4y. And you can see that these two are, one is minus the other. And so we get our Cauchy-Riemann, so the Cauchy-Riemann equations hold. And that is what you'd expect, because you would hope that a polynomial in Z would be differentiable everywhere, and indeed this confirms the fact. Well, this tells us that if this is differentiable, the Cauchy-Riemann equations hold. It doesn't tell us it is differentiable, just that in this cubic, the real and imaginary parts satisfy Cauchy-Riemann equations. We, of course, would like to be able to go the other way, and I'll come to that in a moment. Just a little challenge problem to, if you want to play with this, to show that in polar coordinates, the Cauchy-Riemann equations take this form. And so you can just do a change of variable on the partial derivatives and show that that's what the Cauchy-Riemann equations look like in polar form. Now, if we further assume that u and v have continuous partial derivatives of all orders, a remarkable fact that will follow later from the differentiability of f, then from the Cauchy-Riemann equations we can differentiate the first equation. So I've got u sub x as v sub y, so differentiate them both with respect to x. And this one is equal to v sub xy because the partial derivatives are continuous, so you can swap the order of the differentiation by Bernoulli's theorem. And this one, of course, by Cauchy-Riemann just equals minus u sub yy. And that means then if I take this one plus this one, I get 0. So I get u sub x plus xx plus u sub yy is 0. This is sometimes known as del squared u. And similarly, you can show that del squared v also turns out to be this expression, and that's equal to 0. And this equation, del squared u equals 0, is known as Laplace's equation, and solutions of it are called harmonic functions. So that means the real, and in brackets here the imaginary parts of a differentiable function turn out to be harmonic. And we're going to say that if you've got a differentiable function, so the real and imaginary parts are harmonic, and we're going to say that they are harmonic conjugates of each other. Harmonic conjugates of each other. Now, we would like to, well, here's another challenge problem here, which is a nice problem to do. If you've got a function u plus iv is differentiable at z as x plus iy, And if you take the real and imaginary parts, put u equals a constant and v equals a constant, then you want to show that these two curves are mutually orthogonal. These two graphs of these two curves are mutually orthogonal. And a little hint how to do that: find dy dx for each of these expressions and show that their product is -1. Just as a little example of that, you might like to think of what happens if you take, say, z squared. So if you take z squared, then you get x squared minus y squared plus 2xyi. And if you put x squared minus y squared is a constant, you'll get curves like this, assuming the constant's positive. If you take 2xy is the same constant, again assuming it's positive, this is going to give you some hyperbole. So this is going to look like this. And what we're claiming here is, by this challenge problem for you to do, is that the tangent lines meet at a right angle. And this happens in general. This is just a particular example of this. It happens in general that the real and imaginary parts intersect. So if you put them equal to a constant and draw the pictures, then they intersect at right angles. They're mutually orthogonal. Okay, now just as a little example to finish off this little section, this little video with here, if I give you just the real part, so I'm giving you u of xy is e to the x sine y, I'm giving you the real part, and I claim that this is a harmonic function. We'll just mention that in a moment. So this is the real part of some analytic function, and once you've got the real part of an analytic function, you can reconstruct the entire function you started with. In fact, you can find the harmonic conjugate for this one, and we're going to do more and actually try and guess what the analytic function was that it came from. So firstly, note that if you differentiate this twice with respect to x, it doesn't change. If you do it twice with respect to y, the sine will go to cos, the cos will go to minus sine, and if you add those together, you can see you're going to get 0, so this u is harmonic, and we'll let v be its harmonic conjugate. Now, by Cauchy-Riemann equations, v sub y, whatever this v sub y is u sub x, and we can get u sub x from here. It's just e to the x sine y. And so I can partially integrate this expression here. So the integral of sine y goes back to minus cos y. Now, normally when you integrate, you pick up a constant, but when you partially integrate, you pick up a whole function depending on the other variable, which here is x. So we can partially reconstruct, pun intended, we can partially reconstruct this v by integrating this, and then we pick up a whole function of x that we don't know what this is yet. Now, people do this in various ways. Some people then, what they do is they use the, they do the same thing the other way. That is, they say, they use the Cauchy-Riemann equations and then get another expression for v, and they compare and contrast. I just like to plug it straight into the second Cauchy-Riemann equation. So if I work out u sub y, that gives me e to the x cos y, and this is supposed to be minus v sub x. If I differentiate this with respect to x and put a minus sign, I get e to the x cos y, and then minus phi dashed of x. So these cancel out, these have to match, and I find then that phi dashed of x is just 0, and that means phi of x is just a constant, which I'll just call c. This doesn't always happen, but you will always be able, for an analytic function, or for a harmonic function I should say, you'll always be able to get a formula for this just involving x. Here it turns out to be a constant. Now, since we only want, the question actually says find a harmonic conjugate, so I'm going to just find one. I'm going to put c to be 0 just for simplicity. and that will then give me this function f, which was u, that's the real part, and then the imaginary part we worked out over here was minus e to the x cos y. We're taking this constant to be 0, so I get minus I e to the x cos y. And really that's kind of all you can do with it for the moment, but I'm going to push it a little bit further. I'm going to factor out minus I e to the x out of this, and I do that because that then gives me cos y plus I sine y, and cos y plus I sine y is e to the iy, and we are strongly tempted to add these together using the index laws to get this, and this would be just minus I e to the z. Now I put a question mark here because we don't know what this means at this stage. We haven't defined the complex exponential, and we don't know that we're allowed to do this, in fact, but we'll see later that what I've done here is correct. We just don't have quite the machinery to be able to state that immediately. So, but this is the function that this was the real part of. This was the function this was the real part of. And we'll continue this in the next recording.